Yeah, so welcome to the temporal graph reading group, everyone. Yeah, so thanks for joining the talk today. We are very glad to host uh, Xinyu He um, from University of Illinois Urban-Champaign, who will be presenting their recent work on temporal heterogeneous graph generation with privacy and utility and efficiency. Some notes on the speaker. Um, so Xinyu He is a PhD student at the University of Illinois at Urbana-Champaign, advised by Prof. Um, Han Tong in the um, Idea ECEL Joint Lab, and she earned her bachelor's degree in Tsinghua University. Her research generally focused on data mining and machine learning, and especially graph mining. Her research interest includes different aspects of trustworthy ML and recommender systems, with a current interest of the intersection of the two. And her research also extends to complex graph mining and large language models in recommendation systems. Yeah, so I will let you start the talk.
Thank you for the introduction. So I will start my paper sharing today. The paper title is Temporal Heterogeneous Graph Generation with Privacy, Utility, and Efficiency. This is a ICLR 2025 spotlight paper, and I'm very happy to share it with you guys. So here's the roadmap for my today's presentation. I will first introduce the motivation for our work and briefly.
The first page of the presentation. I'm not sure if you moved the pointer yet. So we don't really
Oh, okay.
just see the PowerPoint, but not the actual slides.
Okay.
So maybe it's presenting on a different screen. Yeah, now
Yes, I'm
yeah,
presenting.
if you click, yeah, present from the
Okay, maybe I will just say in this mode. I turn on
yeah,
the
yeah,
presentation mode, but it seems you can't see the screen. Okay,
yeah, this is good.
okay. So I will start with a brief introduction of the motivation of this work and introduce the methodology, experiments, and finally draw a conclusion for this talk. Before I start, I'd like to introduce the concept of temporal heterogeneous graph. So temporal heterogeneous graphs is one fundamental component for relational deep learning and exists widely in today's real-world datasets. For example, in many relational databases and in many citation network, transaction network, there exists like node type for each node. For example, the node could be user items in recommendation network, could be paper author in citation networks, and also there could be timestamp that's available for our graph mining. So in this paper, we generally model the temporal heterogeneous graph as a series of time snapshots. So each GI here, G1, G2 to the GT, they are graph time snapshots indicating the graph structure for each timestamps. And without loss of generality, we also denote the node types as OI and OJ for node VI, VJ. And also we have other, I think like, okay. And also we are also expressing the ages like VIT, OI, VJT, OJ. So despite the wide application for temporal heterogeneous graphs, we found that a complex topology can increase the potential of privacy leak. Take an toy example from below. So for an attacker that trying to identify a victim that he knows the degree of the victim. For example, if the victim is node 1, so it has degree 1, and there are a total of 3 nodes in the original graph without the information of node type. And the probability of the attacker successfully identifying the victim is 1/3. So, however, if the attacker knows additional node type information of the victim, then in a heterogeneous graph, if node 1, node 3, node 6, 4, and 7 are of the same type, the attack probability will increase to a half 0.5. So this shows that the node type in heterogeneous graph, and also similarly, the temporal information in temporal graphs will increase the potential of privacy leak. I think there's something wrong with the camera, so I will have to turn it off. Sorry for the disturbance. To solve this problem, many previous work aiming at solving the privacy concern use like a perturbation-based method. So this is due to the fact that perturbation can decrease the attacker's confidence. See the similar example below that after perturbation that we only added one new edge from node 3 to node 6. We can see that attack probability of identifying node 3 and node 4 decreased to 0. This is because in the original graph, the node degree of node 3 is 1, and in the new perturbed graph, the node degree is 2. However, the attacker still knows that the victim's node degree is 1, so it cannot identify the node 3 successfully. In this work, we aim to design an error-bound differential privacy perturbation algorithm for the temporal heterogeneous graphs. However, the perturbed graph, although it can increase the privacy of the synthetic graphs, it does not preserve the utility of original graph. And if you think that if we do a lot of perturbations, it could be just some random graphs and is not at all the same of the original graphs. So based on this, let's move on to the methodology. This the POP framework is composed of 4 parts, including a perturbation mechanism that we just mentioned is a error-bounded differential privacy perturbation mechanism, and also adversarial training network, including 2 discriminators and 1 generator that tries to preserve both the utility from the original graph and the privacy from the perturbed graph. So the first part of this framework is the perturbation mechanism. As we mentioned before, we aim to design an error-bounded differential privacy algorithm, which is with privacy guarantee. So first of all, a brief introduction on the edge-level differential privacy. So in the edge-level differential privacy on plane graphs, it defines that given 2 adjacent graphs, which only differs in one edge existence, a mechanism for perturbation is edge-level differential privacy algorithm if and only if the probability of the outputs of the original graph and its adjacent graphs are similar. This indicates that the adjacent graphs become indistinguishable after going through the mechanism M. Therefore, we can say that it preserves the privacy of the original graph because after some twist or flip of the node's attributes, it cannot be distinguished by the attacker. So in this work, we propose the following mechanism to do the perturbation. This is quite a simple mechanism, which includes 2 parts. The first one is adding edges, and the second one is deleting edges. So these 2 are there's no conflict between the 2. The first one is adding edges to those absent edge with some predefined probabilities. And the second step is deleting edges with a predefined probability. Note that when we are deleting the edges, we do not delete the edges that we add in the first stage. So step will prove that the proposed mechanism is a temporal edge-level differential privacy. But given that previous works also only define the differential privacy on plane graphs, we start by defining the temporal edge-level differential privacy. So here we first define the adjacent concept on temporal graphs. So first of all, we define the adjacent temporal snapshots as 2 snapshots that differ in only one edge existence but have the same set of nodes. And then we extend to the adjacent temporal graphs that are adjacent even only if they have the same time span but only differ in one period of adjacent snapshots. Given this definition of adjacent temporal graphs, we extend edge-level differential privacy to temporal edge-level differential privacy. So this definition is quite natural extension of the original differential privacy that we only extended to the temporal domain by enforcing the similar constraint on snapshots. So here we give our theoretical conclusion that the proposed mechanism M that we mentioned before is an epsilon edge level differential privacy algorithm, which is bounded by 2 times max epsilon plus epsilon minus at each t. So here I will not go into the mathematical details of the proof, but I would briefly introduce the general idea for the proof of the theorem. So consider a simpler state that we have that the graph G and its adjacent graph differ in only one absent edge, which means that in the adjacency matrix A of the graph G, there's no edge between node U and V, but in the adjacency matrix of the adjacent graph A tilde, there is a edge between U and V. So the probability gamma here is the probability that after the perturbation mechanism M, the A and A tilde will become the same. So this consists of two states. The first of two possibility. The first possibility is that when we're doing the plus mechanism in M and plus, we add the H to A, and the other ones remain the same. And the other probability that lead to adjacent graph become the same is that when we are doing the M minus, we delete the H from the A tilde. So the after the summation, we can see that both the joint probability of these two possibility is bounded by e to the epsilon plus 1 to e the epsilon plus plus e to the epsilon minus, and this one is bounded by 2 times e epsilon minus. So after we draw this conclusion, we can also consider the opposite side of this assumption that the only difference is an existing edge, that the original graph has the edge UV, and while the adjacent graph A tilde does not have the edge. And combining the two assumptions, we will draw the conclusion of this theory. So although there's no explicit relationship between epsilon plus and epsilon minus, and you can set as it is in the experiments as hyperparameters. But from the data-driven angle, we expect that after going through the mechanism, the sparsity of the graph remains the same. So in this paper, when we are conducting the experiments, we enforce that the epsilon minus and epsilon plus follows the following relationship. So the M here is the number of existing edges in the graph. And so this n squared minus m is the number of non-existing edges in the graph. So overall, this expresses that the number of deleted edges and the number of added edges are the same. So this is all for the perturbation mechanism. So based on differential privacy, the perturbed graph after perturbation mechanism is a privacy preserved graph. So in this, however, as we mentioned before, the perturbed graph can be really random and does not preserve the utility and the distribution from the original graph. So next time we will introduce an adversarial learning network that tries to preserve both the utility from original graph and the privacy from the perturbed graph. So this adversarial network consists of 2 discriminators and 1 generator. So the first discriminator is to preserve the utility from the original graph that try to distinguish the random walk sampled from our original graph and generated by the generator. And the second discriminator is a privacy-preserving discriminator that try to distinguish the random walks sampled from the perturbed graph and generated by generator. And finally is the graph generator that tries to generate synthetic random walks that inherit both privacy from the perturbed graph and the utility from the original graph. So first of all, we try to generate a graph based on sampled random walks. This is because, like in some of the diffusion model works, they generate the graphs based on the adjacency matrix. And however, this can be really space and time consuming because the complexity is all square. But if we if we do the generation and discrimination through the random walk-based method, we can achieve a linear of the scale of the number of nodes. So a random walk in the temporal heterogeneous graph is defined by the following, which includes a set of temporal nodes and also their node types. And we use a LSTM-based sampling process that involves an LST map that has the current state, the memory state, and the hidden states. And generally, we first sample the current node type from the hidden states, and then we generate the sample nodes based on the sample node type and the hidden states. Here we do not add the time superscript of the V, but just keep in mind that it has timestamp going with this node. And the discriminators was implemented with tri-level attention. So we designed this mechanism because the temporal heterogeneous graphs can contain many information, including the structural information from the graph's perspective, and the temporal information and the heterogeneous information. So we try to define a network that can capture all three angles of the information. So we define the tri-level attention as below. So first is the temporal side of the attention network that we use pre-train embedding for the temporal nodes, which is the HIT here for node VI at time snapshot T. And we calculate the attention score between the temporal nodes for the time-based attention. And for the node side that we try to capture the structural information of the graph, we define the representation of the node itself by taking summation over all time snapshot T so that it can represent the overall feature of the nodes over time. So this is the second aspect. And the third aspect is the heterogeneous dimension that we input the node types and try to learn the distribution of the node type along the random walks. So given the structures, we try to train the complex generative adversarial network. So as you may observe, there includes two discriminator and one generator. And given that adversarial training itself can be hard, and having two discriminator can be harder to train, and may have a tendency to collapse. Therefore, when we are implementing our methods, we took an alternative approach by setting utility discriminator as a scoring function, and so that this utility discriminator will be pre-trained and detached from the adversarial learning framework. Therefore, you can see that we removed the training process from adversarial training process of the original graph and generated graph in the utility discriminator, but instead we pre-trained the utility discriminator with the randomly sampled generated negative samples and the sample sampled from the original graph. So when we are doing the adversarial training, we only need to train the min-max game between the graph generator and privacy discriminator. And for the privacy discriminator, we aim this discriminator aims to distinguish the walks from generator and the walks from the perturbed graph to preserve the privacy of the perturbed graph. And the generator tries to fool the two discriminators and tries to maximize their scores from the two discriminators. So as we have finished the introduction of the adversarial network, we assume that we have we have a generator that generates lots of random temporal heterogeneous random walks that follows the distribution of original graph and the perturbed graph. So here we introduce how we can assemble the generated random walks into the final synthetic temporal heterogeneous graph. So first of all, we will sample a lot of random walks from the generator, and based on this corpus, we will estimate the H probabilities and the meta probabilities from that is generated from generators. Then we will sample a metapath instances based on the metapath probabilities, and according to the sampled metapath, we will sample nodes one by one. And finally, which is expressed as the probability below, that we first sample a starting node based on the H probabilities, and then we sample each node at the next step based on the next node type in the metapath and the previous sample nodes and the H probability. So after we sample this metapath instances, we will add all the edges in the generating metapath instances into the generated graph. We did these steps, but instead of directly adding the random walks directly generated from generator to the graph, because we think that the walks generated by the generator can be low quality. So instead, we want to summarize the output and the knowledge from the generator and extract the synthetic generated graph from all the distributions, from the underlying distribution of the generator. So as we introduced in the previous sections, the perturbed graph is differential privacy insured. So in this part, we claim that the synthetic graphs that is generated by generative adversarial networks is also privacy insured. So this is because that in previous work, generative adversarial network have already been proved that it can be interpreted as concerning input and output under differential privacy constraints. This means that if the input graph is differential privacy insured and inputs are ID distributed, the output will be differential privacy guaranteed as well. And as our generator does not touch any real data and the random walks are sampled ID, so the generated synthetic graph from the generated adversarial network is privacy guaranteed under the differential privacy. So next, I will move on to the experiments in this paper. So first of all, as we are the first paper that we know that is studying the temporal heterogeneous graph generation problem and also the privacy aspects, we first designed 7 metrics for evaluating the performance of our model. So the measures can be categorized into 4 types. The first one is measuring the plane graph utility that include the mean of degree distribution, discrepancy. And the second one is from the temporal aspects that we calculate the maximum mean discrepancy distance of several statistics, including the clustering coefficients, size of the largest connected components, and triangle count over the time dimension. And the third aspect is the heterogeneous graph utility, which includes the mean of the cross entropy or probability distribution of metapaths. And finally, as it is hard to evaluate the privacy of graphs, we design a simple matrix that is the ratio of overlapping age compared to the original graph to evaluate the privacy. The motivation for this matrix is that the less overlapping is the synthetic graph with the original graph. The less similar is the synthetic graph with the original graph, the less likely the privacy is to be leaked. So here is the utility and privacy experimental results. The left side, the 6 matrix here are the utility um, from plane graph utility, temporal graph utility, and the heterogeneous graph utility. From the table, we can see that we reach competitive performance compared to other 6 strong baselines, which includes heterogeneous graph generation, temporal graph generation, and diffusion-based graph generation. And from the privacy column, we can also see that we reached the lowest overlapping rate on the datasets, and so that we reached the best privacy compared to the baselines. As we only have a simple matrix in the purpose table, we design additional experiments to confirm the privacy preserving performance of our model. So like in the previous toy example, we designed a node query attacker that the attacker knows the degree of the node and is trying to identify a victim. So in this setting, the nodes sharing the same degree with the target victim will be possible candidates. So the probability of attackers successfully identifying the candidates is 1 over the number of 1 over number of nodes that share the same degree of the victim nodes. And we also consider another setting that is a bit more complex, but also still a simple setting that take the heterogeneous information into consideration, that attacker has a special interest for a certain node type, and so that only the nodes sharing both the same degree with the target node and the same node type with the victim node are possible candidates. So in this case, the probability of successfully identifying the target victim is 1 over the number of nodes that have the same degree and node type. This is in the case that the generated graph that the victim node in generated graph has also the same degree and node type as in the original graph. If the node type of the victim change or the node degree of the victim change in the new generated graph, the successful attacking rate will be 0. So here's the experimental result for the 2 setting. We can see that we greatly reduced the successful attack probability, and in in all 4 datasets. And note that except for the heterogeneous graph generation baseline, we add a new baseline here for the experiments specifically. This is the DPGAN network that is the latest differential privacy preserved generated adversarial network. So this one also preserve the differential privacy of the input graph, but is not for temporal heterogeneous graph. So, but this is a strong baseline as of the privacy dimension. And also, as we are doing compared with the diffusion-based models, as they use the adjacency matrix-based sampling, and we use a random walk-based sampling process, you can see that we achieve impressively more effective running time, and we use much less GPU memories in our experiments. So from all 3 experiments, we can summarize that our model achieves high efficiency, privacy, and competitive utility. And an important hyperparameter for our model is the epsilon that controls the number of edges to be added and number of edges to be deleted. Here we did a parameter study for this parameter. So with regards to the age overlapping rate, that indicates the privacy. So the trend from privacy budget from 1 to 4 follows our assumption that when the privacy budget increase, the number of added ages and deleted age will increase. So the overlapping rate will also decrease. This follows our intuition and assumption. However, an interesting thing that we observe is that when the privacy budget increase to a certain thresholds, in this case, when it's about 4, the age overlapping rate will instead actually increase. This is due to that as we are doing min-masking while having the utility discriminator as a soaring function. If the privacy budget is very large, the input preserved graph will be like mostly random, and the privacy discriminator will cannot learn anything useful. So in the min-max game, the penalty from the utility discriminator will dominate the training of the generator, and therefore the generated graph will lean towards the original graph, therefore having a larger edge overlapping rate. So this is all for the paper, and I will quickly draw a conclusion for this paper. In this paper, we propose a temporal heterogeneous graph generation algorithm with privacy, utility, and efficiency called the PUF. And this framework is theoretically privacy guaranteed, and it has high privacy, efficiency, and competitive utility. And our framework can successfully reduce the attacker success probability, and the framework can scalable to graphs with up to 1 million nodes. That's all for the present for this paper. Any questions?
Yeah, thank you for the excellent presentation. So not too much question from my end. If the audience have some question, please feel free to unmute yourself and yeah, and ask the question.
Yeah, I have a question. Thanks for a great presentation. Really interesting. So what are some applications that you could see? So, is it something like if you have sensitive data and you want to release it, or in what situations do you have this attacker framework where they know something about the users?
I think for applications, so differential privacy is a general privacy guarantee. It does not consider any specific attacking scenario. So generally, from the privacy side, no matter how attacker knows about the user information or those information, the differential privacy can guarantee that after the perturbation, the generated graph will be hard to distinguish from the original graph. The adjacent graph is hard to distinguish. So it preserves a general privacy. So there's no specific privacy setting for this work. And for application, yeah, I would say that for some scenario that need to preserve the user sensitivity information, yeah, that's one of the application scenario, possible application scenario. But any other privacy concern scenario can also be their application.
Cool. Thank you.
Thank you.
Hi. As a follow-up, I'm curious about why you've elected to use knowledge about the degree of a node as the basis for attacker knowledge. I understand, of course, you just described that it's the privacy guarantee is more general than adversarial knowledge of node degrees, but I'm curious about why that example in particular was interesting.
There's no particular reason for that. We just select a simpler attack scenario for testing our model. There could be many attack scenarios, but for evaluating our model, we can only select one, and so we select a simple one to analyze that. But in general, the age overlapping rate can be a metric for evaluating the general privacy performance.
Got it. Thank you.
Great. Yeah, so thanks for the nice discussion. I think we are, yeah, I think there's quite a few questions in discussion, so that's good. So I have one final question, and then so here you mentioned that so you're able to scale two graphs with 1 million node and so on. How do you imagine this can scale to like even larger graphs with potentially 10 millions or tens of millions of nodes?
Okay,
Like what would be the
so
main constraint?
okay, so in our experiment, the scalability is mainly constrained by the computing resources that we use. So we use a V100 GPU that has 32 gigabytes, and like we see here, and we have 7, 12. Okay, so this is for the smallest data set. Okay, but so the GPU memory is one of the main constraints for this work. So first of all, if you have larger computing resources, surely you can scale to larger graphs. And on the other way around, I think it is also able for distributed computing. So like we can distributedly compute so I think this is okay for parallel computing, that we compute the discriminator on different GPUs, and also we can store the sort of embedding from the locally and distribute them to different GPUs. So I think parallel computing can be also one of the possible solution if you are scaling up to much larger graphs for a more efficient computing.
Yeah, thanks for the nice answer. And I think that's definitely one way to go about it. And yeah, so let's thank the speaker again. And yeah, thanks again for the interesting talk. And we will see you at next week's reading group. Thank you, everyone.
Thank you.
Thank you.
Thanks.
Bye.
Bye.